One question about the homework.
Yeah.
We need to give a formal proof for the answers that we think are true, the true false.
No, it's just more like some sort of argument. Like for example, if you say that it's false, like you could give an example of matrices that show the
Yeah.
property is false.
Yeah.
And if it's true, it just like just I guess like some sort of like justification, but nothing too like detailed, if that makes sense.
Yeah.
Yeah. So yeah, it's not that. I mean, it is. This class will have a couple true false questions or conceptual problems, if you want to call them like that, but it's not. It's never going to be something like hyper like technical, where like like the argument would require like a couple of paragraphs or something like that. Usually, it would be like 2 or 3 lines or whatever, like just to give some sort of like justification for why that's the case. Anyone else? Good. Okay, so yeah, today we're going to talk about systems of linear equations. Just before we do that, let me just quickly give you a couple of properties of the transpose and the inverse that I forgot to. Well, we didn't have too much time to write last time, so let's just start there. Okay, so here's the first one. Most of them are kind of natural. Let's see. The first one says that if you have two matrices, well, I mean, here when I write A plus B, I'm already assuming that you can add them together. Otherwise, it wouldn't make too much sense to write the property as I'm about to do so. But what this property says that is like if you have two matrices, you add them and then take its transpose, right? That's the same as taking the individual transposes and adding them together. I mean, which kind of makes sense if you remember the transposing. Essentially, what it does is like change your mind about what you're calling columns or rows. Oops, let me just put this under that disturb. Otherwise, the problem with technology is that now everything is synchronized. So you get like a FaceTime call or whatever, all the devices will start like making noises. Okay, the next one, which is also natural, is that transposing once and then another time should just get you back to the original matrix, right? Because you're changing your mind twice, and so you just get back to where you started. Then this one, okay, this one probably would require some justification. If you take a product of two matrices, of course, here when I do that, I'm already assuming you can multiply them. Otherwise, why would you even write that? It actually ends up being the same as taking the transposes and then their products, but you just have to reverse the order. Okay. So that one is actually important. So let me put this because it's not like maybe so obvious that you would like just like the first two probably even if I had not written them out, you kind of like on your own would have written that like, but this one maybe it's not so clear maybe why that's the case. At least let me, I don't want to spend too much time like. The thing is, like, some of these proofs are kind of tedious because it's just playing around with sums. A multiplication of matrices is just a bunch of sums of products of like the entries. So if you have seen some notation with this sigma thing, if you have done series or in Calc 2 or things like that, then yeah, like the proofs can be done very elegantly. But if not, you just have to put dot 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 dot, and like you don't gain too much like insight by putting dot 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 everywhere else. So I'm kind of want to skip those, but at least let me tell you why it kind of makes sense. why you would expect that based on the size of the matrices. So for example, if A had been like, like M by N, right? And B had been N by L, right? Then I'm allowed to do the product of these two, right? And the product AB would be like N by L, right? So when you transpose that, AB transpose, oops, let me put it next to it. AB transpose, remember, it flips the size of the this would change the size of the matrix, so it would be L by N. Okay, so that's what you would end up with. And what happens if you do? So if you look at B transpose and A, on the other hand, like A transpose would be N by M, and B transpose would be L by N, right? So you see, you cannot multiply the transposes like in this order, A transpose, B transpose. It wouldn't make sense necessarily because like they don't match up. But if you write it in the opposite order, then B transpose, A transpose would be L by N, N by M, and then you end up with something of size L by N. So at least in terms of sizes, it does kind of suggest that that's what you had to do, because otherwise you would not have been able to take the product. Is that making sense? So A transpose, B transpose would not have necessarily made sense in that order, but at least definitely in the opposite order, it always makes sense. So like then the other, like the thing that you have to check is that it does give you what you expected, but is that kind of okay? Like that's more of a better insight than just like trying to write like the proof of why this works, like with a bunch of dots, like, because literally that's what we would end up doing. So it's more like of some sort of like size argument based on the matrices. And this is actually useful why, even if you only care about square matrices, it's kind of useful to think about the rectangular case, because if you put like all of the same size, so you cannot see these like subtleties. But when they are like rectangular matrices, then it kind of becomes more obvious that you have to change the order, if that's okay. So rectangular in any case, rectangular matrices are useful. But I'm just saying, even if you only care about square matrices, like some of these properties become more clear when you try to make sense out of them for the rectangular case. Okay. So again, this is kind of important. And then we have the other ones, like we have similar ones for like the inverse, that A inverse, okay, this is kind of like natural as well. It should just be A, that kind of makes sense. And of course, again, when I write it, I'm assuming already that A is invertible to begin with. Otherwise, why would you even, like, that property would not make sense. And then there's like this analog for the inverse of two matrix instead of the transpose. So if you have like AB, you multiply them and you take their inverse, assuming that all of them are invertible, that would just be B inverse A inverse. Okay. That one, let me put it, let me box it again, because it's an important one. It may not have been that obvious. And this one is, the argument, first you can, they are all squares, so for them to be invertible to begin with, so you cannot just like run an argument like the one that I did here. But remember that the property of an inverse is that like an inverse is a matrix that when you multiply it with the matrix you care about, you get the identity, right? So if the matrix I care about is AB, right, and I multiply that by B inverse A inverse, well, the thing is like now B is B inverse, right, and they cancel each other out. So you get like A identity, A inverse. And then, well, identity is kind of like one. You can put it if you want or not when you're multiplying, so you forget about it now. And again, A, when it is A inverse, they cancel each other out. So you get identity. So you see, from there, you see that you have to write them in this order so that like the cancellation could occur. Because if you have written A inverse, B inverse, then there's no way to do any cancellations. Is that kind of making sense? So that just tells you that this matrix has a property that when you multiply by this one, gives you the identity. So it has to be the inverse of the product matrix. Okay. And the last property, which is the last property that I wanted to mention is that like the inverse and the transpose actually interact in a nice way. So this is also an important property. So if you take the transpose of a matrix and assuming everything is invertible, let me put it like this. If you take the inverse of a matrix and then transpose that, that's the same as having transposed first and then take its inverse. So let me, in words, taking inverse and then transposing is the same as transposing and then taking inverse. So taking an inverse and then transposing is the same as transposing and then taking inverse. That making sense? I mean, again, another to give you like an idea of why that would be true if you're interested. Like most of the these proofs are kind of like quick, but they can be a bit confusing when you see them the first time. Like the idea is like the A times A inverse has the identity, right? Right, that's a property of the inverse of a matrix. And then if you transpose both sides of the equation, that gives you, it's kind of like transposing. You can like when you have an equation between matrices, you can, when you have an equation between numbers, you can take square roots on both sides or take absolute values on both sides or square both sides of the equation. Kind of like there's something similar going on with matrices where you can transpose both sides of an equation involving matrices. Okay. So, but what is the A inverse transpose? That's kind of like the transpose of a product, right? So if you remember, like the property here is like it is a transposes, the individual transposes, but you just like switch the order. So it's A inverse transpose, like A transpose. And what's the transpose of the inverse? If anyone remembers?
It'll just be the matrix.
Sorry, should not say the inverse, the identity. I don't know if I have been saying the inverse. I mean the identity matrix. So, sorry. Yes, the identity is its own inverse, so it's not too bad. It's like it's and it's all transpose, by the way. So, but so that means that here's a matrix and here's another matrix whose product gives you the identity. And so one is the inverse of the other. So from here, so it looks kind of weird, but that means that A transpose it, let's see. So the inverse of A transpose, like it has to be like the matrix that when you kill it, gives you the identity, so it is a inverse. Because again, when they see each other, they give you the identity, so one has to be the inverse. But you don't have to worry too much about those proofs, but it's kind of like to give you like a sense of how they work. They're not that long, as you see, but it kind of needs a little bit of a meditation to use. That is kind of like doing what you want them to do. So, I mean, take them as a black box. These two are kind of natural, important, and important, right? So three are kind of okay, and three are kind of like you really need to remember because they may not be so obvious. Is that okay? Any questions about this? Okay, so now we move to this other part about linear equations, finally. So we're ready to talk about systems of linear equations.
Where does a projector come from? I don't remember.
So as an example, let's write this as, so here's an example of what I mean. So imagine that someone had asked you to try to solve this system, right? And like, I mean, you have seen like things like this before, maybe. You could use like, maybe if you want like the first equation, like this is kind of like the traditional approach of what you may have done. You could have taken the first equation to say, well, x is y minus 1, right? And then you substitute that in the second equation, and then you solve for y, and then once you now have the value for y, you go back and plug that into the equation for x, and that's how you would find the value for x and y. That's not what we're going to do. We're going to do something a little bit more systematic. But let me just say that if you were to solve it in some of these ways, you would get, and like again, we'll see how. So like the solution to this system ends up being x equals 2, y equals 3. That makes sense because if you do 2 minus 3, you get -1, right? So the first equation is satisfied. And then if you do 3x, you get 6 plus y, which is 3, you get 6 plus 3, which is 9, right? So that's how this would look like. So here's now what we have to do is like interpret this system of equations in some ways that are useful for us to think about it. So here's like one interpretation. And I'll call this the geometric interpretation. I mean, the okay. Well, if I call that, it will spoil the. I'll reserve the name for a second. If I say the name, I kind of spoil everything. So, what does this equation represent on the XY plane? Yeah, well, same for this one, right? So that like the line interpretation, that's what I wanted to write. But if I can say that, like, it ruins everything. So the line interpretation is that, well, you could think of the first equation as some line. I mean, secretly, like you're used to think about these equations as in terms of y. So notice that this first equation says that y equals what? X plus 1, I think. So here's x minus y equals -1, or y equals x plus 1. They're the same. And the other one, again, like secretly saying that y equals 9 minus 3x, right? So one had like positive slope, the other had negative slope. And well, I don't know, it kind of looks like this, right? So this is like the other equation. So the point 2, 3 actually corresponds to the intersection of the lines, right? I mean, that's the whole point of solving the system, to figure out whether the lines intersect or not. So solving the system is equivalent to finding whether the lines would intersect or not. Does that make sense? To finding the point of intersection of this line. Is that okay? So far, so good. So maybe you remember this from high school geometry or somewhere. When you have two lines on the plane, so when you have two lines on the plane, what can happen? They can intersect at one point, which is what you see there, right, in this picture. So option one is that they intersect at one point. So like an example of that would be x minus y equals -1 and 3x plus y equals 9. What's another thing that could happen when you have two lines on the xy plane besides intersecting at one point? Yeah, they could be parallel, and if they're parallel, that really means there's no intersection, right? So no intersection, like parallel case, good. Parallel lines, I should say. What would be two parallel lines is like the slope one thing, right? So let's put 2x plus y equals 9 and 2x plus, I mean, doing it very simple, but equals 5. I mean, it's kind of obvious that these two, if you write it this way, it's kind of silly, because it looks like, oh, you're saying 2x plus y has to be 9, and at the same time it has to be 5, right? So obviously it won't have a solution. But if you were to plot this, it looks better because it literally will look like two parallel lines, right? So here's like one solution, right? here's 0 solutions, right? And there's actually a third case that it kind of seems very silly, but still you can mention it explicitly if you want, which is kind of like like the lines are secretly the same. Like, so like you kind of are repeating the same line. So you're over counting the line. So like the lines are the same. So for example, if I had written 2x plus y equals 9 and 4x plus 2y equals 18, right? If I had asked you to solve this system, right, this equation is the same as that equation, right? I just multiply every side by 2. So they're secretly just one equation. So it's kind of like an illusion that you have two lines. They're just really the same. So actually, like since if I give you if I ask you to solve the system of equations, you cannot just find like a unique solution because any point on the line would solve the system. So what I'm trying to say is that here you would get infinite solutions. And what I'm trying to say is that there's really like a sense in which everything that is going to happen in linear algebra, like this is not unique to this case of two lines, like all the solutions will either be 1, 0, or infinity. This is like what always happens. Like I will try to explain that with more detail soon. But this is like kind of like the general case. So the general case is that when we're solving a system of linear equations, we'll find either 1, 0, or infinite solutions. Nothing else happens. Like you can never find just 10, for example. It is like you'll see it's kind of so this is kind of what happens in general. This is the general behavior pattern. General pattern where there's only 1, 0, or infinite solutions for any system that we're going to work with. For a system of equations. One, 0, or infinite solution. So before like explaining that in more detail, let me give you another example. Here's another example. Example number 2. Imagine that I ask you to solve so again, if you have never seen this before, you can try to do something similar. Like you could take the third equation to solve for x, right? Once you solve for x in terms of y and z, you plug it into the other two equations, right? And now you have a system with two equations, two unknowns, and then you kind of work on it in the same way as before, right? Like you solve, like do substitutions or something else to get the values. So again, we'll find like a more like systematic, like, you know, general, like a way to do it that it kind of is more like consistent every single time, so that you need less creativity on how to solve it. That's what kind of what we're aiming for. But for now, let's say that you did that and you would end up finding that you find that the solution is and by that I literally mean that if you know you plug in this so this is -2 and -2. So by that I just mean that if you plug in these values in the equations, you get like an equality, right? So just do it for the last one because just it's easier. So -x becomes -1 plus 1/2 y becomes 1/2 y. So you get -1, -1, so that gives you -2, but then minus z becomes +2, so that gives you 0. Right, so that's how the third equation is solved, satisfied, and then all the others kind of work in similar ways, right? So if you plug in those numbers, those values for x, y, and z, you should get like that the equations are satisfied. But okay, there's kind of like a similar interpretation for what's going on here. So here's like one interpretation of the system. Okay, so we know that this looks like a line. This equation looks like a line. Anyone knows what an equation of this sort looks like? It looks like a plane, which you may or not have seen before. So let me show you what that is like. Okay. So there's this GeoGebra thing, which I really like in general. So there you can go to the you just go to geogebra.org and you can click on the 3D calculator if you want to play with it on your own, and you get thrown to something like that looks like this. So let me see if I have the equations here. So the first equation was 3x plus 2y minus z equals 1, right? So that's your first plane, the blue one. Okay, this let me see if I can hide. I don't want to show the XY plane. It will be confusing. So let me move it to the HDMI because I don't want to be showing the. Otherwise, like you'll see the XY plane, which is kind of confusing. So here you go. Oh, good. I need to share. Oh, I haven't opened GeoGebra. Let me open. Is it? Well, I have to move it around. Okay, now I have it here. So where is GeoGebra? Here you are. Is this the one that I'm sharing? Let's stop the share. Yeah, that's fine. Yeah, now it looks good. So you can go on GeoGebra also to the 3D graphics view. It's also, it's nice, it's more convenient to have the one on the computer, just because, like, for example, now I can hide the XY plane from showing, which is what I wanted to do in the online version. So you put 3x plus 2y minus z equals 1, which is the plane that you were seeing before. So a plane is just like an infinite piece of paper. So you get then 2x minus 2y plus 4z equals -2. And okay, now this is getting confusing, and you change the color. And this should allow me to change the color, and now I don't know why. Nothing is working. I was supposed to. Yeah, but why is my keyboard does not work? What's going on here? Okay, in a perfect world, this would allow me to change the color, and now I don't know why. But okay, it's going to be a little bit more messy. But can everyone? Okay, so you have like a plane, you have another plane, right? And do you see what the intersection of those two things is looking like? Anyone wants to take a guess? Yeah, so like in general, like the intersection of two planes is a line, good. And then you had the other plane, which is in here. So you see these three pieces of paper, right? Yeah, okay. Yeah, I don't know why this is not working. So you have these three pieces of paper, and then the intersection, like this point of intersection, which I found or I wrote before, is 1, -2, -2. If you see it there, which is this blue point, and so for some reason it's not allowing me to make it bigger. So in general, like it would allow me to work with it, change the colors and everything. I don't know what's going on today, but that essentially gives you the point of intersection of these planes. So like the idea is like solving the system of equations corresponds to figuring out whether the planes intersect. Okay, so when you have two planes, they intersect. If they were to intersect, it would be like a line, and you kind of hit it with another plane, and like it's kind of finding an intersection between that line and this third plane, if that makes sense. And that does give you a point. So let me write that down on the board. Okay, so this looks worse. Like it's not working. But just readjust the screen. Yeah. Okay. No. So the interpretation here is like the plain interpretation, right? Um, which is basically the solving the system is equivalent to finding the intersection of the planes, right? Solving the system. To finding the intersection of the planes. And then I mean, this is maybe something you have thought about less, but then you have to ask, well, what are like how do like the intersections between planes look like, right? So like the intersections between planes, it could be one point, right? Kind of what we just saw. So it could either be one point. Then you could have, for example, no points of intersection that happens, like say, like the planes are parallel. Like there's like a way in which to make the planes parallel, so they wouldn't touch one another. So there could also be no point of intersection. For example, with parallel planes. And finally, there could also be infinite solutions if, say, you repeated one of the planes secretly, right? Like kind of like what we did with the line. So maybe like I gave you three equations, but two equations representing the same plane. So you end up getting like a line of intersection, and so like that would be infinite solutions. So like infinite solutions. Well, for example, if you repeat one of the planes and they intersect, which intersects the third one at a line. Another one at a line. Does that make sense? So, I mean, I only mentioned this to show you that it has like the same structure as before, 1, 0, infinity, right? 1, 0, infinity. And like kind of like the story goes on more or less the same way. If like you had four like system with four unknowns, right? Like here there were like three unknowns, right? X, Y, and Z. So you had planes in that case. When there were two unknowns, you had lines. So you had lines and you had planes, and you had like four variables, for example, X, Y, Z, W. I mean, you don't give like a specific name to those, you just call them hyperplanes for what it's worth. So they like then you have to think how they look like, but you can kind of, I mean, after some practice, you can kind of visualize a little bit how they're supposed to look. You just need like a fourth dimension, right? Because like now there are four variables. So, but like philosophically, the same is happening, so they would intersect, and so they could maybe just meet at one point or never meet at all if they are parallel, these hyperplanes, or they maybe are like infinite solutions if they happen to be the same. So in general, like what I'm trying to say is that for all these systems of equations, we only have like this, one, like for all the equations we're going to be solving in this course, it's only, you're ever going to find only one, none, or infinite solutions. Nothing else will ever happen. So if you find something else, you did something wrong in the process. Okay, so it's kind of making sense. Okay, so this is like the way to think visually of what's going on geometrically with these planes. Let me give you another interpretation. Okay, here's another interpretation for what's happening. And actually, this is one of the most important ones. So let's call this, again, well, if I say the name, I kind of spoil a little bit of the surprise. So let me not give you the name for a second, but it's kind of like very cool as well. So let's go back to the system of like that I started with, which was this one. Okay. Now, well, there was a reason why I started with matrices, right? And this course. there's a way to rewrite this as a matrix. This should be a 2 by 2 matrix, right? Because there's two variables, two equations. So what are the coefficients that I should put here? Anyone remembers how to read off the matrix from equations? I think we did this briefly once.
1, -1, 3, and 1.
Good. So if you do that, you get this. And for example, let's do it for the other one as well. If you remember, well, the one that I gave you with the planes. Right. Now I can rewrite this as XYZ, right? 1, -2, 0. And what numbers do I put now for this matrix? 3, 2, -1, 2, -2, 4, and -1, 1/2, -1, right? So this is our matrix A in this case, right? This is our matrix A in this case. So like the more elegant way to think about these systems of equations is that instead of like thinking about it like as a bunch of separate equations, right? You kind of like put them all together in terms of a matrix, right? So now just as a thing of notation, like this is what I have been calling before, like the vector B, right? If you remember B, and there it would be B. It's kind of like traditional for this to call it like a vector X, because it's kind of like it looks like a vector of variables, right? Unknowns. So you kind of give it like you call it X instead. So like this is called like A the times the vector X. It's not the variable X, it's like a vector. Okay, and again, this instead of being called B gets called X. Okay, and so this looks like A times a vector equals another vector. So that vector, I mean, had to be given a name, and I guess like people wanted to go alphabetically. So this is just called the vector little p. So so let me write that down. So for us, a system of equations, like a linear system of equations, is a set of equations that can be written as AX equals B, where A here is a matrix, right? Where A is a matrix. It's a matrix. X is a vector of unknowns, like variables, or X is like a vector of variables. So X is a vector of variables. So like, for example, again, it could be like XY or XYZ. And usually we won't do more than 4 variables in this class. I mean, just to keep it like kind of simple. So it could be XYZW. But I mean, you can imagine how it would go. If you had 10 variables, like you don't want to run out of letters of the alphabet. So you just call them X1, X2, X3, X4, X5, X6, X7, X8, X9, X10, right? because you don't want to like keep thinking about that. And B is kind of like a vector that's given to you, right? Vector given. That okay so far so good? Is that making sense? Yeah.
Is the vector of solutions, they typically have a solutions already.
It is kind of right. Like that's another way of thinking about it. If you that's like a good point to make. So if you like the diagrams that I have been doing in the past, you know, it's not now you can think about it this way. Now you have the process A, right? I know that the output is a vector B, right? And I'm asking you kind of like, oh, can you find the input that you have to feed into the machine that will spit out the vector B? So it's kind of like, you know the output, can you find the input for me kind of question. So like, right, from this perspective, it's maybe more clear. Like you have to, like now we think that the input, that the output is known, and we're trying to find the inputs that would give you that output, right? So now here, like this perspective is, the output B is known. And we're trying to find if there's like a input that produces it, right? And it's kind of like what people call like a reverse engineering type thing question. Like, you know, you're going backwards in a sense. We're trying to find like the input X. Does that make sense? So, right, in a sense, like solving a system of equations is kind of going backwards from that perspective because, and here it's kind of like the end result, -1,9, that's the end result. And we're trying to find like, what did you have to feed into the machine that would give you that end result? Okay. So yeah, that's a cool, also like a useful interpretation, which I mean, just feels very different from thinking, oh, I'm like finding where lines intersect, right? Like this has like a different flavor to it. Like it's just like in terms of a process. So far, so good. Any questions about this? Okay, so here is another way, and there's like that's the thing about this class. Like we're just doing a bunch of products, but like we're just thinking about like these equations in like many different ways. So here's still another way to think about what's going on. So we had like 1, -1, 3, 1 times x, y equals -1, 9, right? And again, if you were to do this product, this is, well, x minus y, right? And then 3x plus y equals -1, 9. Which kind of makes sense, right? Because if you equate the entries, that's how you get back to these equations, right? So that's fine. That's how this is supposed to work. But now I'm going to do something which looks a little bit odd, which is I'm going to break this vector into two pieces. One piece has everything that involves x, and another piece has everything that involves y. Okay, so what's everything that has x? It is x and 3x, right? And what is everything with y is negative y and y. So now it looks like this. It kind of seems stupid because why are you breaking it up? But you'll see that it's actually useful. But for now, let's just bear with me to see that this is a useful thing to try. So is everyone okay with why this equals that? Right, so I just broke it into all the stuff, all the jump with x goes to one vector, all the jump with y goes to another vector. Now, why do you break it in these terms? Because since the first vector has all the stuff in terms of x, you can factorize like an x, pull it out of the vector. So it looks now like x times 1, 3 plus y, and you can do the same for the second vector, right? Y times negative 1, 1 equals negative 1, 9. Right? Now this equation looks like this. Now what's this vector 1, 3 in terms of like the regional matrix? What does this correspond to? This is the first column, right? So this is column 1. Good. And well, the other one is column 2, right? So here's something like it's kind of like hidden on what we're doing. That from this perspective, let me see, I have the cute picture on the notes here. Okay. So from this perspective, when I'm sorry, I should put column 2 below. So from this perspective, like trying to solve the system means like, can you take the columns of this matrix, right, and combine them, right, in such a way that you get the output, right? You have the columns of the matrix, which are two vectors, like I'm about to draw them, but you have the two columns, right? There are some vectors, and I'm asking you, can you combine them? By combining, you just add them, right? So that you get this other vector that I care about, but like the combination is allowed to be, rescaled. So if you remember, like multiplying a vector by a number just rescales that vector, right? So what I'm asking you is like, can you rescale the vectors if needed and then add them together to get the output? And that's what I'm about to call like a linear combination in like 5 minutes. But let me draw a picture for you of what's going on. So what I'm asking is like, if you take the vector 1, 3, which is in the first quadrant, right? Then the vector x times 1, 3 is just like a rescaled version of it, right? So you can draw like something that looks like this. This is kind of like how x 1, 3 looks like, right? It points in the same direction. It's just that maybe bigger or smaller depending on what x is. So what I'm asking is, can you take this new vector and then take the vector coming from column 2? Column 2, like negative 1, 1, that's in the second quadrant, right? So negative 1, 1 looks maybe like this. And again, like the rescale version looks like this. And so the question is, can you add these vectors together, right? So that you get the blue one. Let's call this like the output one. That's also in the second quadrant. So from this perspective, what I'm asking, so here what I'm asking is, can you combine the columns of the matrix to get the vector B? Like, can you combine a rescaled version, right? Can you combine the rescaled version columns of the matrix? Um, to get the vector v. Okay, that making sense. So from this perspective, like solving a system of linear equations is just asking you whether you can express the output, right, in terms of the columns of the matrix, which is kind of like very important idea to have in mind. So let me just write that down here. So here's like here's an interpretation of this is called the column interpretation of the system of equations. The column. So like what I'm trying to say is that if A is like a bunch of columns, let's call them column one, a vector of columns, column one, column two, column three, up to column n. These are like the columns of A. And X is like x1 up to xn. X1 is like x1, x2 up to xn. Let's put it even x3 explicitly. X1, x2, x3 up to xn. Then this system is the same. This means the same. This means the same as x1 column 1 plus x2 column 2 plus x3 column 3 dot xn column n equals 3. That make sense? Okay.
X1 column 1, is that a sum?
X1 column 1, you mean this thing?
It's plus, so it's a whole expression.
Right, this means multiply the column by x1, add it to the second, do x1 times column 1 as a multiplication, right? Add that to x2 column 2. Add that up to x3 column 3. Let me write it, okay, let me put it, let me put this as another example to make this more concrete. So, and like just to make sure that you don't think I'm being biased, I'll put more variables. So let's say this is like x minus y plus W equals 3, X plus Y plus 2Z equals 4. And then let's put another one, which is like I'll put all of them 2x minus y plus z plus 3w equals 5. Okay. I like this example just because now it won't be a square matrix. So it's kind of useful to get used to it. And I'm going to follow like an alphabetical order. Well, it's not really alphabetical because W is going to come after Z, but you know what I mean. Like it's going to be X, then Y, then Z, then W when I rewrite this system of equations. So there's going to be, what I'm trying to say is that you can rewrite this in a matrix form. In which way? X, Y, Z, W, right? Then 3, 4, 5. And then just identify, let's say identify the coefficients. So what's multiplying X in the first row or first equation is 1, right? Then you put -1. What should I put for C? 0, because I don't see it, right? And what should I put for W? 1. And then I put 1, 1, 2. And now I don't see W, right? So I should put 0. And then I put 2, -1, 1, 3. Is that okay? So hopefully it's like going from here to here eventually will become like a piece of cake, right? Like it's super, like should become supernatural eventually. Maybe not right now. But so solving the system of equations, and this is like a 3x4 matrix, right? So this makes sense because this is 3x4, and then this is 4x1 if you want to think about it as a matrix. So you can do the product and you get something which is 3x1. So all of this makes sense in terms of sizes, matrix multiplication, or whatever. Okay, so this is like our A. This is our X, and this is our B. So far, so good? Is everyone okay with this? Now, what I'm trying to say is that from this perspective, right? This is like actually one way to think about this thing is kind of like you take this vector, put it like rotate it and put it on top of the matrix, right? So X lands above this first column, Y lands above the second column, Z above the third column, and W above the fourth one, and it kind of works the same way. So that this is equivalent to X 1, 1, 2 plus Y -1, 1, -1 plus Z 0, 2, 1 plus W 1, 0, 3 equals 3, 4, 5. Okay, is that better now? So this is like what I mean by x1 column 1, x2 column 2, x3 column 3, etc. So this is what, like in this notation, is what I'm calling column 1, column 2, column 3. Is that okay? And so what this question, like again, there are many ways to think about this system. Like one way was like, well, this is like some sort of hyperplane because it has 4 variables. So it is like you have one hyperplane, another hyperplane, a third hyperplane. You're asking, do they intersect? And it's like when they intersect, does this point 3, 4, 5 belong to that intersection? But an alternative way, which is maybe more convenient because you can actually represent these vectors because they have 3 entries, so you can represent them in space. Is like, can you re-express this vector as a sum of these columns? But you're allowed, the game allows you to, you know, rescale them a little bit if you need to. So it's not that you have to take them like as they come. You can say, well, I don't want to work with the column 1. I want to work with 2 column 1. Like you can, but you have to keep their directions because multiplying by a scalar, it doesn't like change the direction, only the size of the vector, right? So the game is like, can you kind of like rescale the vectors and then add them so that you get the desired one that you want. Is that better now? So that's called, and in this case, you say that this vector is a linear combination of the columns. So today, let me just finish with this definition or notation. Here we would say, but I mean, the word combination is kind of like maybe clear, like because you're combining the vectors by adding them. So here we say that, here that B is the linear combination of the vectors C1, C2, C3, C4. If this can be solved, or I mean, if you can solve the system, if this can be solved, we say that B is a linear combination of C1, C2, C3, C4. Okay. So in general, like maybe just finish up with this definition. So in general, a vector B is a linear combination of some vectors B1, B2 up to Bn. If you can express B as a sum, so if you can write it, if you can find numbers x1, x2 up to xn, such that B is the sum, or let me put it this way: x1 b1 plus x2 b2 blah 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 plus xn bn equals a vector. Okay. Or in a more concrete way, which is my favorite way to say it, in other words, if you can solve this system, in other words, you can solve AX equals B, where A is formed, where the columns of A are the vectors B1 up to Bn, where the columns of the matrix A are the vectors B1, B2, Bn. Okay. So, I mean, this is kind of a little bit too abstract for now, maybe. We'll talk about linear combinations a lot more after the first midterm. So there's not too much, I would say, to worry about them for now. Except knowing that if you, like, I'll give you some problems to think about it. But if I ask you, can you write a vector as a linear combination? I'm secretly asking you, can you solve a system of equations? Basically, that's all that I'm trying to say. So next time we'll finally, like next week, we'll finally get into the business of actually solving these systems. But you'll see that solving this system of equations is actually like a piece of cake. So it is, I mean, except like just for the fact that it's kind of tedious sometimes because there are many equations. Like there's no major science to solving a system of equations. So like the important thing is kind of to understand that there are many things that are happening at once. Like you're finding if some things intersect, lines, planes, or you are finding if some vector is a combination of other vectors. I mean, there are many things going on when you solve a system of equations, but like solving it itself is kind of like not that bad. So next week we'll start, yeah, I'll start telling you how to do that, and then we'll be actually, as I was saying, very strict on that. So, now that we have done a lot of matrix stuff, so, yeah, I'll see you next week. I'll post another assignment for you to think about, over the weekend. Um,